folks, this is Rifat Bari, Brown University graduate student in physics. Today, I welcome you to the next episode of General Relativity. In previous episodes, we talked about tensor algebra, where we learned how to do three operations with tensors: addition, multiplication, and contraction. These are the three operations that constitute tensor algebra. Tensor algebra. Today, we are finally ready to make the leap onto tensor calculus, which is going to be our main tool along with differential geometry for general relativity. Tensor calculus is going to tell us how a tensor changes over the surface of a manifold. So let's say that I have some kind of a surface. If I have a tensor, let's say I have a vector here, and I transport that vector along some curve. How does that tensor change as I move it along that curve? Is that tensor going to stay in the same direction, or is it going to bend as I start approaching the minimum of my manifold? These are the types of questions we'll start being able to answer in this episode. So that's the big idea. Today we're going to start tensor calculus. But what's the smaller idea? What is the small idea we're going to start with today? The idea today is a dictionary. Okay, so let me explain what a dictionary is. Let's say you're in another country. Let's say you're in Europe, in Italy, and you need to talk Italian. Okay, so somehow you're a person who only knows English. You only know English. But somehow you have to speak Italian. How do you go from English to Italian? Well, you need something called a dictionary to translate every letter of the English language into Italian. Dictionary. Similarly, let's say you're in one coordinate frame, let's say Cartesian, and you want to translate into an easier coordinate frame, let's say polar. Okay, how do you do that? Well, you need a dictionary. You need a dictionary. And today we're going to figure out the language of dictionaries using tensor calculus. How do you go between two, not just Cartesian and polar, how do you go between arbitrary reference frames, arbitrary coordinate frames? What if someone hands you a random coordinate basis with original coordinate bases E1, E2, and they ask you to give you the dictionary that will take them to the new coordinate bases E1 prime, E2 prime. So the goal of this lesson, the goal of this video is to figure out how to find the dictionary between two coordinate bases. That is the goal of today's lecture. So let's dive right in. Basis vectors are just the building blocks of ordinary vectors. So let's draw an example here. So let me zoom in to my mini coordinate plane here. And let's say I have some vector. This yellow vector v can be decomposed into its x and y components. There's an x basis vector here. Let me call it x hat. And there's a y basis vector here. Let's call it y hat. So we can say that this vector v can be written as some amount of the x hat vector, let's say 3 of the x hat vector, and some amount of the y hat vector, let's say 4 of the y hat vectors. What that means is that we'd have to put 3 of these x hat vectors together and 4 of these y hat vectors together, 1, 2, 3, 4, to assemble this general vector v. So that's the idea of basis vectors. And now today we're going to generalize basis vectors into tensor calculus. So what does that look like? Let's take a look. In tensor calculus, it turns out that it becomes useful to denote these basis vectors not as just vectors, but as partial derivatives. In other words, I hat, the x hat basis vector, can be written as partial r, partial x. And similarly, j hat, the y direction basis vector, can be written as a partial derivative of some vector with respect to y. So let's start with the coordinate system. Here's my x-axis, here's my y-axis, and let's say I have two vectors. So I'm going to use blue. Here's my first vector, let me call it r. Let's say I have a second vector, r sub h. let's say that r, this vector r, is located at a point x comma y, and that this vector r comma r sub h is just one unit over in the x direction. So what does that mean? That means the difference between these two vectors is going to be r sub h minus r. Now, how can I write that in a more mathematical format? Well, I can just say that this difference, r sub h minus r, is equal to the difference between these two vectors. The first vector is r sub h, located at x plus 1 comma y, minus the vector at r, located at x comma y, and divide by the length of the difference between these two vectors. The difference in the coordinates is simply 1. Delta h is 1, or delta x is 1. So okay, this is one way that we can write the difference between these two vectors. And you might say, okay, so what's the big deal here? Well, now let's take this a step further. Now, let's zoom out and let's take the same idea. Let's say we have another coordinate system once again. Here's my x-axis, here's my y-axis. And once again, I'm going to say that we have our two vectors r. But now, instead of drawing, so here, I used to draw r over here. Instead of drawing r sub h over here, I'm going to bring it a little bit closer to r. Okay, so here's r sub h now. And now their difference is a little smaller, you might say. This is the difference between our two blue vectors. Now, what's another way I can frame that difference? Well, I say that the difference between my two vectors is simply, well, first of all, what are the coordinates? Let me put down the coordinates. Let's say that this r vector is at the same location, x comma y, but this r sub h vector is at x plus 1/2 comma y. So now, the difference in the x coordinates is no longer 1. That difference is 1/2. Okay, so now we can write our statement here as r sub h, which is located at x plus half, comma y, minus r, which is at x comma y, and divide all of that by half, which is the difference between the x coordinates. But wait a second, if I divide by a half, that's the same thing as multiplying the difference in their lengths by 2. That would actually double this difference vector and get me back to the original vector size that I had previously. Does this extrapolate? Well, let's see. Let's take this a step further. Let's say now, once again, I have my x and y coordinates, and now I'm going to bring my vector r even closer. So let's say, let me zoom up here to the blue vector. So here's my r vector once again at the point x comma y. But now I'm going to bring r sub h even closer. Let's say I bring it over here. Here's r sub h, and now it's located at the point x plus 1/4 comma y. Now the difference in these two vectors is very small. It's just a quarter. That's the difference between their x coordinates. It's just 1/4. Delta x is 1/4, and so that means r sub h minus r, what's that going to be? That's going to be, first of all, r sub h is now located at x plus 1/4 comma y, and r is located at x comma y, and let's divide this by a fourth. But dividing by a fourth is the same thing as multiplying this difference by 4, right? And so that means the length of our vector is going to quadruple, and so our vector is going to be multiplied in its size 4 times. And so check it out, the vector is going to again be the same length as it was originally, right? And so what's the moral of the story here? The moral of the story is that no matter how small we make this difference between r and r sub h, the length of this vector r sub h minus r is going to stay 1 unit, right? And so if we extrapolate this, just take our imaginations a little bit further, then let me grab the red marker, then we can say that r sub h minus r is equal to, well, it's r sub h of x plus h comma y minus r at x comma y, these are both vectors, divided by h. And now let's, instead of putting r sub h 1/2 or 1/4 or 1/8 away, we can just make it infinitesimally far away. In other words, what we're taking is the limit. We're taking the limit as h approaches 0. So let me put a limit as h approaches 0. And so now you might be starting to get the sense of what we're trying to do. You see, r sub h minus r is not that important, but what is important is that this is in the same direction as the basis vector I had. In other words, this is our basis vector e sub x. And so, another way that we can frame what we just discovered is that the basis vector I had, or e sub x, can be written as the limit as h approaches 0 of r sub h of x plus h comma y minus r x comma y over h. And what is r? R is just some kind of a position vector. And so now, what is this limit if not a derivative? So our basis vector e sub x, our basis vector in the x direction, can just be framed as the partial derivative. Let's make sure I get this right. The partial derivative of r with respect to x. Okay, that's the big idea. And so, for an arbitrary basis vector e sub I, that basis vector can be written as the partial derivative of a position vector r with respect to that direction I. There you go. That is the general definition or the general derivation for a basis vector in tensor calculus. Now let's try to use this idea to come up with the dictionary between two coordinate frames. Let's talk about how we transform between two different bases. What do I mean by that? Well, let's say you have two languages like English and Italian, like we were talking about in the beginning of the lecture. Or English and, okay, Italian, let's settle for that. Now, to translate between these two languages, what do you need? You need a dictionary. You need a dictionary or Google Translate to go between these two languages. Just like that, if we're in two different coordinate systems, such as Cartesian and polar coordinates, then we need some kind of a dictionary to take us between these two coordinate systems. So let's say that our first coordinate system is E1, comma E2. We need some kind of a transformation, something that'll take us from E1 and E2 to E1 prime and E2 prime. So what we're looking for right now is the dictionary that's going to take us between these two coordinate systems. So how do we do that? Well, let's take a look at first a very simple example. So let's say that you have a coordinate system, or in fact, before we even get to coordinate systems, let me just put some dotted lines in the background. And let's say that you have some original basis vectors on these dotted lines. So let's say that I have an original basis vector e sub 1 and e sub 2. Okay, they're the same length, they're orthogonal, whatnot. Here's e sub 2. Now I have some new basis vectors. Let's draw my new basis vectors. Let's say that here's my first new basis vector, e sub 1 prime. Here's my second new basis vector, e sub 2 prime. The question is, how do I translate between these two basis vectors, between these two coordinate frames? In other words, how do I go between E1 and E2 to E1 prime and E2 prime? That is the question that we're trying to answer. What is the dictionary that will take us between these two basis vectors? Well, to answer that question, in this case, it might be pretty simple. For example, we see that it seems that we need just one of E1. So let me write this down. The question is E1 prime and E2 prime can be written as linear combinations of our original basis vectors. So some amount of E1 plus some amount of E2 can express E1 prime, some amount of E1, and some amount of E2 can express E2 prime. Well, how much of the do we need to create E1 prime? Well, let's see. This is just hand waving here, but let's say maybe 1 E1 and 1/2 E2 creates E1 prime. Just making up numbers here. And let's see. Minus 1 E1 and 1 E2 seems to create E2 prime. So that means if I take one of my E1 vectors and combine it with 1/2 of my E2 vector, then I'll get E1 prime, my first new basis vector. And similarly, if I take minus 1 of my E1 vector and 1 of my E2 vector and combine them, then I'll get my E2 prime vector. Okay, that's the idea. That's what we're shooting for here. Now this is a pretty simple example, but this is the kind of basic fundamentals of what we're going to do as we keep going. Okay, so now let's deal with two concrete coordinate systems, Cartesian and polar, as we discussed in our introduction. So let's say I have a Cartesian coordinate system here in blue, and I'm going to have a polar coordinate system set up here soon. So let me first draw my Cartesian coordinate system. Here is my Cartesian coordinate system, and it has two basis vectors. Let's scroll up and get the blue. The two basis vectors are I hat, or as I'll call it here, E sub x, and j hat, or as I'll call it here, E sub y. These are the two basis vectors in the Cartesian coordinate systems. And the cool thing is that no matter where you go in the Cartesian plane, these two basis vectors are the same length and the same direction. Now we shouldn't take that for granted, because as soon as we step over into the polar coordinate system, things are going to start to change. We ask what the basis vectors are here. Well, polar coordinates has a radial basis vector that goes radially outwards. Okay, here's the radial basis vector. I'll call that E sub r. And it also has a theta basis vector, which is tangent to the circle at this point. So that's E sub theta. Let me make that smaller. E sub theta is right here. Now, the strange thing about polar coordinates, or really any general arbitrary coordinate system, is that when you move around, the coordinates no longer stay the same. So for example, if I come over here, the radial coordinate is going to become like this. It's not going to stay in this direction anymore. Instead, it's going to point in this direction. It's going to point radially outwards. And similarly, the theta vector is going to point like this. In fact, it's going to be a little bit bigger. Now, some textbooks, they have a normalization factor for the E sub theta coordinate. Now, I'm not going to follow that because Chris doesn't, and I'm following his notation. So now, what we're trying to figure out is the dictionary that's going to take us from Cartesian coordinates to polar coordinates. What dictionary is going to take us between these two coordinate systems? That's the question. To frame it more mathematically, what we're trying to do is we're trying to figure out how we can combine our original basis vectors to create these new basis vectors. In other words, to state that in an even more different way, what is the dictionary that takes us from the Cartesian to the polar coordinate system? If we can figure out this dictionary here and now, then we can generalize it for an arbitrary coordinate system. So now, let's try to figure that out. What are the scaling coefficients that take us from Cartesian to polar? Well, you see, this is a pretty difficult problem to solve. What we're trying to figure out is no easy task. We're trying to figure out, let me recap, let's try to get the blue marker. What we're trying to figure out is how to go back and forth between Cartesian and polar coordinates. E sub r, nope, that's yellow, let's keep up the color coding here. E sub r and E sub theta. So the question is, what can take us back and forth between these two? Now it turns out it's pretty hard to solve this problem, but it's much easier to solve an analogous problem, which is exploiting what we just learned. Remember that we learned that partial derivatives are the exact same as basis vectors. So why don't we use that to our advantage here? Instead of writing E sub x and E sub y, why don't I write partial r, partial x, where r is some position vector, and partial r, partial y. And likewise, why don't we write, so this is trying to go to the polar coordinate system. Why don't we write, okay, so now this question might become easier to answer, and let's see how. So instead of e sub r, I'm going to replace that with partial r, partial lowercase r. And instead of e sub theta, let's replace that with partial r, partial theta. And now we're trying to figure out, once again, what are the scaling coefficients that's going to take us from polar coordinates to Cartesian coordinates and vice versa. So instead of e sub x, I'm going to write partial r, partial x. Likewise here, partial r, partial x. And let's put the summation over here. And partial r, partial y. Let's switch to blue. Partial r, partial y, partial r, partial y. And now here's the magic. If you can see how to go from here to here, then you have figured it out. You've figured out the problem. You've cracked the challenge. So how do we go from partial r, partial lowercase r to this? Can you figure that out? Well, it turns out here's the answer. What you're looking at right now is the multivariable chain rule staring at you right in the face. You see, this is almost like a full derivative. Not quite, it's a partial derivative because r is a function of multiple variables. But partial r sub r, well, what is that really saying? That's saying how does r depend on r, but lowercase r depends on x and y. So really, what we're doing here is the multivariable chain rule. So this right here, what do I have to write here? Well, it's quite simple. I just have to write partial x, partial r. See, now, I'm not allowed to do this, but if I could, you can see that would just reduce to partial r, partial lowercase r. And likewise, here I will write partial y, partial lowercase r. And now, look how easy, look how effortless the mathematics becomes. I've literally just used the multivariable chain rule to solve the problem that's been haunting us. How do we transform between two basis sets? And so now we have the answer to our question. The way that we transform from Cartesian to polar coordinates is by using these partial derivatives. And in fact, we can write, if you notice, this is a system of linear equations, so we can write this entire thing in matrix form as follows. We can say that e sub r and e sub theta can be transformed to e sub x and e sub y using a simple matrix, and that matrix is called the Jacobian. That matrix is called the Jacobian, and the Jacobian matrix is made out of these scaling coefficients that you see right here. These purple coefficients are the elements of the Jacobian. Partial x, partial r, partial y, partial r, partial x, partial theta, partial y, partial theta. These derivatives constitute the Jacobian, and the Jacobian takes us back and forth between the polar coordinate system and the Cartesian coordinate system. And so folks, that is the beginning of the answer to our question, how do we translate between two different reference frames or two different coordinate frames? Thank you for watching this episode of General Relativity. We'll check you out in the next one.